Every second, trillions of bytes of data are generated from social media, IoT devices, banking transactions, healthcare systems, and more. How do companies efficiently store, process, and analyze this enormous data load? This is where big data architecture plays a crucial role. In this video, we will explore fundamental concepts, different architectures like Medallion, Lambda, and Kappa, and best practices for designing robust data pipelines. Let's dive in. Big data refers to extremely large and complex datasets that cannot be effectively processed using traditional data management and analysis tools. It is characterized by the 3 V's, originally defined by Gartner. 1. Volume. Massive amounts of data generated from various sources. Example, social media, sensors, transactions. 2. Velocity. The speed at which data is generated and processed in real time or near real time. Example, stock market feeds, IoT devices. 3. Variety. Different types of data, structured, unstructured, or semi-structured, such as text, images, videos, logs, and more. Later, 2 more V's were added. 4. Veracity, the quality and reliability of data, inconsistencies, noise, biases. 5. Value, the usefulness of data in deriving meaningful insights. Big data is everywhere. Every time you scroll through YouTube, Google something, or get a personalized Netflix recommendation, big data systems are working behind the scenes to process and analyze massive amounts of data in real time. More examples are business, customer behavior analysis, personalized marketing, healthcare, predictive analytics for disease outbreaks, finance, fraud detection, algorithmic trading, smart cities, traffic management, energy optimization. Before we dive into big data architectures, let's first understand the 3 primary data processing models: batch processing, real-time processing, and hybrid processing. Batch processing handles large amounts of data in chunks. This approach is commonly used for ETL pipelines, report generation, and data aggregation. Real-time processing continuously ingests and analyzes data as it arrives. This is used for fraud detection, real-time recommendations, and stock market analytics. Lambda architecture combines both batch and real-time processing, allowing businesses to get the best of both worlds: historical data analysis and real-time insights.
The Medallion architecture is a data design pattern used in modern Lakehouse environments to organize and process data in layers, improving quality and reliability as it moves through each stage. It is commonly implemented in platforms like Delta Lake, Databricks, and Apache Spark. The architecture consists of 3 main layers. 1. Bronze layer, raw data. Purpose: ingests raw, unprocessed data from various sources, example logs, IoT devices, databases, APIs. Characteristics: data is stored in its original form, JSON, CSV, Parquet, etc. Contains duplicates, inconsistencies, and possibly corrupt records. Retains historical data for traceability. Example, streaming clickstream data from a website. 2. Silver layer, cleaned and validated data. Purpose: filters, cleans, and transforms raw data into a more structured format. Characteristics: data is deduplicated, standardized, and validated. Schema is enforced, e.g., using Delta Lake tables. May include joins, aggregations, and basic business logic. Example, filtering out bot traffic from user clickstreams and merging with user profile data. 3. Gold layer, business-ready aggregations. Purpose: provides refined, aggregated data optimized for analytics, reporting, and machine learning. Characteristics: highly structured, often in star/snowflake schemas. Optimized for fast querying, materialized views, pre-computed metrics. Used by BI tools, Power BI, Tableau, and data scientists. Example, daily revenue reports, customer segmentation models. Key benefits of Medallion architecture. 1. Scalability, handles large volumes of structured and unstructured data. 2. Data quality improvement, each layer enforces better data integrity. 3. Flexibility, supports both batch and real-time processing. 4. Cost efficiency, stores raw data cheaply in bronze layer while optimizing high-value data in gold layer. Mentioned are the comparison with traditional data warehousing. Example implementation, Databricks Delta Lake. Bronze, ingest raw JSON logs into Delta tables. Silver, clean data, enforce schemas, deduplicate. Gold, create aggregated tables for dashboards, example, monthly sales by region. This architecture is widely used in cloud data platforms, like Azure Synapse, AWS Lake Formation, GCP BigQuery, and is a best practice for modern data engineering. Lambda architecture is batch plus real-time processing. Lambda architecture is a data processing framework designed to handle massive scale, fault-tolerant data systems by combining batch processing, for accuracy, and real-time stream processing, for low-latency insights. It was introduced by Nathan Mars to balance speed, scalability, and reliability in big data applications. Key layers of Lambda architecture are: 1. Batch layer, cold path. Purpose: processes historical data in large chunks for accuracy and completeness. Characteristics: high latency, minutes to hours. Runs on distributed systems like Hadoop MapReduce, Spark. Outputs master datasets, immutable, append-only. Example, daily sales reports, user behavior trends. 2. Speed layer, hot path. Purpose: handles real-time data streams for low-latency insights. Characteristics: low latency, milliseconds to seconds. Uses stream processing engines, like Apache Storm, Flink, Kafka streams. Produces real-time views, approximate but fast. Example, fraud detection, live dashboards, alerts. 3. Serving layer, merge results. Purpose: combines batch and real-time results for querying. Characteristics: merges batch views, accurate, plus real-time views, latest updates. Uses fast-read databases, like Apache Druid, Cassandra, HBase. Example, showing total sales today, batch, plus last 5-minute sales, real-time. Now let's see how Lambda architecture works. 1. Data ingestion. Incoming data is sent to both batch and speed layers, example, via Kafka. 2. Batch processing. Processes full datasets periodically, example, every hour. 3. Real-time processing. Handles latest events immediately, example, fraud alerts. 4. Query serving. Applications query both layers and merge results. Advantages and disadvantages of Lambda architecture. Pros: fault-tolerant, batch layer recomputes if errors occur. Scalable, handles petabytes of data. Balanced, combines accuracy, batch, plus speed, real-time. Cons: complexity, maintaining two pipelines, batch plus stream. Latency in batch, not suitable for ultra-fast decisions. High operational cost, requires two separate systems. Modern alternatives. Kappa architecture, pure stream processing, example, Apache Flink. Delta Lake/Lakehouse, unified batch and streaming with ACID transactions. Now let's move on to Kappa architecture, streaming first approach. Kappa architecture is a simplified alternative to Lambda architecture, designed for real-time data processing by using a single stream processing pipeline instead of separate batch and speed layers. It was proposed by Jay Krebs, creator of Apache Kafka, to reduce complexity while maintaining scalability and fault tolerance. Core principles of Kappa architecture. 1. Single stream processing pipeline. All data is treated as immutable streams, no separate batch layer. Historical data is reprocessed from the event log when needed. Uses stream processing engines, example, Apache Flink, Kafka streams, Spark streaming. 2. Event sourcing and log-centric design. Relies on a durable, append-only log, example, Apache Kafka, Pulsar. Events are stored permanently, allowing reprocessing at any time. 3. Reprocessing for batch-like analytics. If business logic changes, the system replays historical data from the log. Avoids maintaining two separate codebases, unlike Lambda. Now let's see how Kappa architecture works. 1. Data ingestion. All incoming data is written to an event log, Kafka. 2. Stream processing. A single stream processing job consumes and transforms data in real time. 3. Output to serving layer. Results are stored in a queryable database, example, Druid, Lakehouse. 4. Reprocessing, when needed. If logic changes, the system replays past events from the log. Now let's see Kappa architecture advantages and disadvantages. Pros. Simpler than Lambda, no dual pipelines, batch plus stream. Real-time first, all processing is low latency. Reprocessing capability, enables batch-like recomputations. Scalable and fault-tolerant, built on distributed logs, Kafka. Cons. High dependency on streaming tech, requires robust event logs, Kafka. Reprocessing overhead, large historical data may take time. Not ideal for all batch workloads, some analytics still need batch processing. In any big data architecture, how and where you store your data plays a critical role. That's where the concepts of data lakes and data warehouses come in. Let's start with data lakes. These are vast storage repositories designed to hold raw, unstructured, semi-structured, and structured data at any scale. Think of it as a central place where all your files, logs, JSONs, videos, or CSVs, just flow in without a rigid schema. Tools like Amazon S3, Azure Data Lake Storage, or Google Cloud Storage are commonly used to implement data lakes. On the other hand, we have data warehouses, designed for structured, cleaned, and processed data. Here, performance matters. These systems support analytical queries with lightning speed using defined schemas and optimized storage formats. Popular solutions include Snowflake, Amazon Redshift, and Google BigQuery. So, what's the key difference? Data lakes are flexible, scalable, and cheaper, but need proper governance. Data warehouses are performance optimized for BI tools and reporting, but may cost more and require structured data. In modern architectures, many organizations use both, combining the flexibility of a data lake with the power of a warehouse, a concept known as the Lakehouse architecture. In the world of big data, computation frameworks are the backbone that make large-scale data processing possible. Let's start with Hadoop, the pioneer of distributed data processing. Built on the MapReduce paradigm, Hadoop allows data to be processed in parallel across multiple nodes. While revolutionary, it has limitations. It's batch-oriented, often slow, and lacks flexibility for modern analytics use cases. Enter Apache Spark, a game-changer in big data processing. Unlike Hadoop, Spark performs in-memory computation, drastically increasing speed and efficiency. It supports not just batch processing, but also real-time data streams, machine learning, and graph processing, all in one unified engine. Now let's talk about Databricks, a modern cloud-native platform built on Apache Spark. It offers a collaborative environment for data engineers, analysts, and scientists. With auto-scaling, optimized Spark clusters, and integration with Delta Lake, Databricks simplifies the complexity of big data workloads and makes the Lakehouse architecture a reality. Each of these platforms has its strengths: Hadoop for cost-effective storage and reliability, Spark for performance and flexibility, and Databricks for unified, enterprise-scale analytics. As organizations scale their data infrastructure, security and governance become critical. In this section, we'll explore how enterprises protect sensitive data, enforce compliance, and manage access in big data environments. Big data environments pose unique security challenges: large-scale distributed storage, diverse data sources, real-time data processing, and regulatory compliance. Without a solid strategy, data breaches and non-compliance can lead to severe consequences. Managing access control is crucial. Organizations use role-based access control, RBAC, and attribute-based access control, ABAC, to ensure only authorized users can access specific datasets. Identity and access management, IAM, solutions, such as Azure AD, AWS IAM, and Google Cloud IAM, help enforce these policies. Encryption is the backbone of data security. Data is encrypted at rest using AES-256 and in transit with TLS/SSL. Additionally, data masking techniques help anonymize sensitive information, ensuring privacy without compromising analytics. Regulatory compliance is a non-negotiable aspect of big data governance. Frameworks such as GDPR, HIPAA, and SOC 2 define strict guidelines for data collection, storage, and processing. Organizations implement audit logs and monitoring tools to maintain compliance. Big data platforms integrate security monitoring tools like SIEM, security information and event management, and anomaly detection systems to identify and mitigate threats in real time. These solutions use machine learning to detect unusual patterns and prevent attacks. To ensure a secure big data environment, organizations must follow best practices, implement access controls, encrypt data, ensure compliance, monitor threats, and regularly audit systems. A well-governed data infrastructure is the foundation of trustworthy analytics. Now that we've explored the architectural foundations and technologies behind big data, let's dive into how they're applied in the real world. Across industries, big data is transforming the way businesses operate, make decisions, and innovate. In companies like Amazon and Flipkart, big data platforms analyze petabytes of user interaction data to deliver real-time personalized recommendations. Spark and Databricks are used to process large clickstream data and train ML models that predict user preferences. IoT sensors stream data from machines into data lakes. Using real-time analytics with Spark Streaming or Flink, manufacturing companies can predict failures before they happen, minimizing downtime and saving costs. Banks and fintech companies ingest streaming transaction data and use advanced models to detect anomalies in real time. Kafka, Hadoop, and Spark MLib are common components of this architecture. Hospitals use big data to analyze medical records, wearable data, and clinical trials. These insights enable predictive diagnoses, personalized treatment plans, and operational efficiency. And there you have it, a complete journey through the world of big data architecture. From foundational concepts to real-world use cases, we've explored how technologies like Hadoop, Spark, Databricks, and architectures like Medallion, Lambda, and Kappa come together to build modern data platforms. If you found this video insightful, make sure to like, share, and subscribe. Your support helps me create more deep-dive tech content just like this. Got questions or want me to cover a specific topic in more detail? Drop a comment below, I'd love to hear from you. Until next time, stay curious and keep building the future, one data pipeline at a time. Thanks for watching.